Okay, I'm interested in two different problems.
Okay.
One problem is that I have something, I call it X, that I don't know. Okay. Then I have a model that reads X, call it G of X, and maps it into something else, which I call Y. Okay. This I can observe, so I collect measurements. So I call them D that measures this Y. And then I want to find X. Okay. This is the classical inverse problem. How to estimate X given this nonlinear function of X that gives you Y that you observe. Normally this X is huge, so X is a Rn and it's big. This D is a Rm and M is much less than M. So that means it's an underdetermined problem. Okay. I have many more unknowns than I have conditions in the measurements. So I need to say something about the prior information. I need to add some prior information about X. And that we normally do by, say, you have knowledge of this, the probability density function, I call it f of X. And then I will also use a likelihood function or probability for the measurements to introduce the Bayesian theory. So I say that f of the data given X is a probability that describes this. So I will work with these in the continuation. Then I have another problem, and that is a time continued or the time dependent one. So this is a static problem. There's no time in there. It's an inverse problem. Now I'm looking at, I have some kind of prediction. I have an estimate of a state variable. I call it X up there. And this X is again of high dimension. This is a R. Okay. And I kind of mark it with this point here. And this is at a certain time, so this is at Tn. Then I make a prediction of this X, so I get the new value of X here at Tn plus 1. At this time I have measurements, so here I have Tn plus 1, and I want to combine this D with this X to create a new value of X, which if the measurement is located here, and this is my prediction of X here, then I would expect that my update is somewhere in between, right? So I get a new value of X here. So I want to compute this update. And then I will continue integration, get a new value of X here, I have a new measurement, and I will compute a new update, like this. This problem we can solve using the ensamble filter, for example. It's a sequential data assimilation problem, and in this case you will specify covariances, or you need to know the uncertainty of X, you need to know the uncertainty of D. So you have X and you have this covariance CXX, and you have a covariance CDD, and then you have the Kaplan filter equations to compute the updates. So this is straightforward. So what I will talk about today is something called iterative smoothers, or iterative ensemble smoothers. And what these methods can do is to solve both of these problems. And I will explain how that's done. Okay, so that's the background. So the way we formulate it, here I'm talking about the parameter estimation problem, that's this problem here. So I have my X, I make a prediction Y. There's no time, okay? But I compute Y as a nonlinear function of X. And I have measurements of Y. Measurements have some errors, and I write a Bayesian formulation for this problem. And what that says is that I'm starting from x, the prior distribution for x. I make a prediction for y, so this is just a model, okay? And then I should have touched the card. Something will happen. It's a smart board, right?
Yeah.
And then I have the likelihood function. And if I multiply these together, I get the posterior density of x and y given the measurements. And this is the standard problem solved for example, in reservoir history matching, in updating reservoir models. Is there anyone in the reservoir community here now today? No. Okay. So that is completely irrelevant. Let's look at this data assimilation problem again. Because I said that here you have x at time tn, this, and you make a prediction to n plus 1, and there's a model describing this transition, right? And that's the n of xn that gives you xn plus 1, okay? So that's our nonlinear model. That's the one we have here. Okay. So you start, if you look at the measurements, you have this y that is measured, and it's related to this prediction by the nonlinear measurement functional. Okay. So that just takes the model prediction and projects it onto the measurements. And it can be nonlinear. And this xi plus 1, that's just n of x, so it goes in here. And this is just a nonlinear function of xi. Okay. And I can call it whatever I want, and I call it g of x. And then you see that then this equation becomes exactly the same as we had for the inverse problem here. It's just the same equation. I equals g of x. And then I can use the same Bayesian formulation, but now I start with xi, I make a model prediction, and observe the model to get the predicted measurements y, and I multiply with the likelihood, and have a posterior GDF again. And this is what I would call a smoother update step in sequential data assimilation. So I said that you can compute this update using only this x and this measurement to get this updated value. And that you can do with ENKF or standard counter filters. So ENKF would be the ensemble method for solving this problem. If you look at what's here, what you do here is to use this measurement to update this x. Okay. And as soon as you have done that, if you know this x, you can predict again. So now I'm looking at a different way of updating. So I have the time here. I have my x, my estimate of x here. I run a prediction to get an updated x. Then I have a measurement of d, and then I use this measurement together with this prediction to update this x here. And then I run again, and I get something which is in between the measurement and the forecast. So this is an indirect update, okay? To use Socrates analogy. It's not a direct update. Direct was here, this is indirect. And then, why would you do this?
To avoid imbalances.
Yeah, that could be one reason. At least it would help. In the previous presentation by Jonathan. Yes. Then, what he's worried about is that this prediction will be very non-Gaussian. Okay. So he says that, okay, if this prediction has a PDF that looks like this, then it's not Gaussian. And these ensemble methods, or the ensemble cover filters, will fail. What we do know is that, even if you start with something that's Gaussian here, and you integrate with the model, m of x, here you can get something that's non-Gaussian. And that's a problem, right? So if it's something that will happen if you have a nonlinear model and maybe a chaotic model and you integrate for a long time. If you integrate for a short time and you start from a Gaussian, then it will be almost Gaussian. Okay? So you have small deviations. If you integrate for long times, you will have this problem. But the nice thing here is that now we have a Gaussian prior for D, it looks like this, and we have something that's almost Gaussian at the previous time. And this indirect update will work then only with the Gaussian functions. So the assumptions in the update scheme are not violated, okay? And so what happens if you can update this one, and then you can integrate again, and for the ensemble camera filter, this is a way of improving the results. Well, that said, the other thing, this method will also work well with nonlinear system if you have many updates, okay? Because then, if you run your model system freely for a long time, you end up with these multi-model distributions. But when you start updating, then you are pulling your solution towards the right attractor or the right minimum, right? So you are following the true state observed by the measurements. And if you have sufficient amount of measurements, then you will keep all your organizations close to this reactor in time. And then the Gaussian methods, ensemble methods will work quite well. Yes?
But in a smoother case, you are using observation D in time T plus Tn plus 1, and the forecast state in N plus 1, 2 to predict
backward in time.
Yeah, but you are using a low Gaussian distribution to.
This one.
Yeah, in both cases, in ENTF or smoother, you are using the.
No, but this one is only used to compute the difference between its innovation, right? The measurement minus the. They're not using the distributions.
Okay, so you are using the distribution in time.
So, but okay, so one more thing now. This equation is not really the one we want to solve. This is the joint posterior PDF for x and y. So you want to get rid of y and just update x, okay? So then you can integrate over this one and get y out of the equation.
Summing?
Summation.
I think that maybe you can use so.
Oh yeah.
That's the one way. No, that's okay. Here we go. That's okay. Yeah. So what we do is that we ended up with we have this equation, and then if the model is perfect, there are no errors in the model, then it means that this f of yx can be written in terms of a delta function. Okay. So if you put this delta function in here and we integrate over y here, then we end up with this standard expression, which is just the prior for x, and it's the likelihood function, but related to the x value. Right? So you get your modeling here. Okay. And that's the one we use when we derive the cost function that's used in 40 bar or in these inverse methods for history matching, etc. Okay. So this is the one that we work with. Yes. This is just an example. I used it. It kind of shows the user interface in the software the rest engineers are working with. And here I just kind of put the equation variables on top of the information I have in this user interface. So here, let's say that you have a 4 model, which in this case is Eclipse, which is a reservoir simulator. So that's represented by G. Then they have parameters, which here is porosity and fault multipliers, which is a very simple example. That's the X. And Y, that's the predicted measurements. It's the prediction of oil production, water production, gas production in the different wells. So what I want to do here is to use this information to infer something about the parameters in the model. So it's this problem here. Okay. If go back to this function here, and we put in a Gaussian representation for the errors in the data and for the errors in the prior. Then maximizing the posterior PDF is the same as minimizing this cost function. This we have learned yesterday and the whole week, okay? So this is the standard cost function. You have some prior information on X, and you have the measurements, and you want to minimize the misfit between an estimate of X, weighted with the inverse of the covariances, the measurements here for the prior here, and this is the difference between the measurement and the prediction based on X. Okay, so this is what we want to minimize. Okay, the nice thing with this is that if this G is linear, then there's an exact solution of this equation. This exact solution is the Kalman-Filter equation. So it's this one. If you have your prior, you have your measurement, you compute the prediction here, you have the difference, this is the Kalman gain, then this is the exact solution. And you can also compute an exact equation for the posterior uncertainty, or posterior covariance, given by this equation. The simplest way to visualize what you do with the ensemble Kalman-Filter is to say that instead of solving this equation, you solve it many times. Okay? You have a large number of realizations now, you mark them with J, and you solve exactly the same equation, except that for D you have a TJ, so you have perturbed measurements. So you have a sample representation for your measurement, with mean equal to the real observation, and the spread is given by the uncertainty of the measurement. You have a sample representation of X, which is with mean equal to the real prior, and the spread is again given by the error covariance of X, CXX. And then this is a pure Monte Carlo method of updating all these realizations. So if you take the mean of this equation, you get back this X8, which is the same as you have here. And the covariance is also converging to exactly the same equations you have here. So it's just a Monte Carlo representation of this particular problem. Okay, so, and then the next nice thing is to note that these solutions here is obtained by solving this ensemble, minimizing this ensemble of cost functions. So you can define an ensemble of cost functions where the prior is the prior realization for X here, and again you have the perturbed measurement. So here you have, if you have 100 realizations, you have 100 cost functions to minimize. And if you just compute the derivative of this, you get back this equation in the linear case. So in the linear case, there is a unique correspondence between all these equations. In the nonlinear case, it gets a bit more tricky, because, and also one more thing, in the linear case, solving a number of such minimization problems will give you posterior samples, or no, will give you samples of the posterior PDF. So we are exactly sampling the PDF from base. So in a way, it's a good way to compute samples of the PDF. In the nonlinear case, they will give you approximate samples of the posterior PDF. And this approximation is what we will try to make less important using iterative structures. Okay. So we will work with this equation. We will try to minimize this cost function. We know that in ENKF, you just go directly to solve it like this, and then you have used some linearization to get there. With the iterative methods, we will try to find the minimum, exact minimum of this cost function, or at least get much closer to it. That's what we are getting into now. Any questions now before we? Let's. I think I showed these slides earlier in the week as well, but this is just an example. And this is my predicted measurement. It's called Y, and this red PDF is non-Gaussian. Okay, it's not multimodal, but it's non-linear, so it's non-Gaussian. And I have my measurements represented by the green one, And the black is the theoretical solution. That's what I should aim at getting. Suppose now that I use the EAKF. So I made a prediction Y, I have a measurement of Y called D, and I have an ensemble of predictions, right? I have a sample by X, and I get a sample prediction, I have a sample of measurements, and I update each of these for Y directly. And this is then just a direct update, okay? So I have a prediction of Y, and I'm trying to update it. And then I have this CYY in here, which is determining this update. You don't have the JP okay. Yes. Okay. So then let's see what happens if I compute this update. This dashed line is the ensemble common filter update, or the ensemble common filter update. And it's quite far from the theoretical solution. Okay, so obviously we have a problem, and this is what we will deal with now. Let's use the smoother and try to do this indirectly. Okay? So we made a prediction, a measurement, and then I update xn here, and I integrate again. So I start x, predict y for all the realizations, and I ensemble of measurements, and now I update x. And the only difference is that now I have x, y in here. So this is the correlation between the prediction and my previous x. So there is a regression, or statistical regression from my prediction and back to x that's used to compute this update. And when I have my new x, I just integrate again. And if you look at the result in that case, I get this full blue line here. So now it seems like the mean is almost in the right place, okay? The variance is still not perfect, but it's significantly better than what I had in the EAKF update. And from my understanding, the reason it's so much better is that I'm not working with non-Gaussian PDFs in the update scheme. So, okay. Just have to see what's coming next now.
So here I have a question from the previous slide. You have the cross covariance of x and y, right?
Yes.
But x is a state, y is an observation.
Yeah.
But how do you correlate states which are coming from a numerical model with observations that are coming from a sensor?
No, I'm using the modeled correlations. I'm predicting y.
Okay.
So I'm computing correlation between the predicted y and
the previous. Okay.
Yeah. So it's a time correlation basically.
It's a time correlation. Okay.
Yeah. Yeah, and this is just how it is done in the reservoir. So you start with a prior for x, this red one, so you have x here. You make a prediction, you get the prior prediction for x, which is non-linear because y, g of x is non-linear, right? We combine this with this likelihood function to update x, and then you make a new prediction of x here. So that's what you will do in a reservoir. Yeah, so I'm basically repeating what I've said so far. We use this Gaussian assumption on the priors. So you assume that the priors for x are Gaussian and also the errors in the measurements are Gaussian. That gives us the cost function in this form. The prior misfit, and we have a data misfit. And I will discuss two methods now. Ensamble smoother is this last indirect update, and iterative ensamble smoother. That's a way of improving the results. The ensamble smoother is doing one step, right? It's just it's using a gradient from this equation to go all the way back to x, make one update, and then make a new computation. The iterative smoother is aiming to minimize this cost function exactly by iterating using a Gauss-Newton method. So we'll show the difference. So, okay, when we derive the ensemble smoother, I said approximately solves the gradient equal to 0. So what you do, you compute the gradient. It looks like this. So this term is simple, right? That's just a square, and you have the prior part. This is for the likelihood, and in here you have now the gradient for the tangent linear model of your original model. So you get this in here. The problem is that you cannot solve this for x because you have g as a nonlinear function of x here. So you have to do something more, right, to be able to solve it. And what you do is to express g of x using a Taylor expansion like this, and this capital G is again the same as the tangent linear model defined here. So by linearizing this term, you put this in here, then you can actually solve the equations for x. The other problem in here is that this term here is dependent on the realization, right? Okay. So you have one tangent linear model for each realization. It's the derivative of your model evaluated for each realization. And who knows how we could use this directly? Because that was discussed, if not today, at least earlier in the week. It's the adjunct, right? It's just if you use the adjunct model, it's a way of computing these GJs individually for each realization. My problem is that in most of the application I'm working, I don't have the adjunct. I don't even have the model equations. I just have a simulator that reads some inputs and generates some output. So you also use this linear regression approximation, or we call it a least square fit to represent G. So it's a statistical estimate of G based on your ensemble. And if you insert all of these, and in addition use ensemble representations of the covariances, this is the ensemble smoother algorithm. So you sample your initial ensemble from a Gaussian, you sample your measurements from a Gaussian, mean XF and CXXF here, and the measurement or real observation and the covariance there. Then you integrate all of these realizations over in time to make a prediction. You compute an update based on the Kalman-Filter equations, but now you have CXY here, so you go back in time if it's a time problem, or you, And when you have the new value of x, you just integrate your model again to get y. So this is the ensemble smoother used in this indirect update, or in the inverse problem, if you like. It will be exactly the same. And I guess this is one approximation, and it has an impact. I'm not going to discuss that too much today. This is a serious approximation, because if you are going a long step, then the linear approximation of your model is not good. Okay.
So in that equation is with G, the first one, is not
this one.
Yeah, it's not G of XF.
No, I said G of x in the estimate.
Yeah.
Is given as Gx in the prior x plus G times this residual, the distance between them. So that means, and then you have neglected higher order.
But it's not with G? The first step? Yeah, the first part.
G of x, yeah.
Yeah, equal to G of XF.
This is like a Taylor.
Yeah, it's, sorry. I shouldn't write here, but there should be a G.
Yeah.
G, yeah.
Evaluated.
Yes. Okay. Sorry for that. Well observed. Okay, so let's continue now. Iterative ensemble smoothers, we want to minimize this cost function. And we are going to use a Newton method And then we need a gradient. So this is the same gradient as we had before. And we need a Hessian. And it's just the gradient of the gradient. So I just work like this now. And this is an approximate gradient because you neglect the second derivatives of g from here. That will come from there. So this is actually symmetric and quite nice. And it's what we want to use to normalize and rotate the direction of the gradient in the Okay, so but it seems like if you can do this, then we have an iterative method that should converge towards the minimum of this function. So I know we have expressions for these, so in principle we should be able to do this. Again, the problem is that we have to evaluate all these terms. We have integrated models for each realization to get this one. We have to evaluate this term again, which is evaluated for each realization. Again, we could use the adjoint, which we don't have. Okay, so let's see what is next.
So here I have a question. So basically the gamma value,
this kind of it's just a steplet.
Yeah, you can use a line search or something like that, right?
You can use lots of things.
Yeah, but the point is that in present, in the context of line search, I should like linearize the observation operator that each iteration about the current solution, right?
Also, the cost function is non-linear, and I think normally it's wise to go with a bit shorter step length to avoid not ending up in wild places. There is an issue. This is not just a function; it's a model.
Yes.
So if you have two strong updates of parameters in your model, then it might not converge. You're not able to run the next iteration, even if mathematically the ideal value for gamma is 1. But that in the linear case it will converge exactly to the minimum, right? But we used to tune this one in different ways. We also use lower formulations that kind of changes then you have two parameters. And then what you also want to do is to gradually introduce the information from the measurements. So you start with weaker updates, and then you kind of when things start converging. And that has been shown to increase convergence also. The problem now, this is the gradient. And it looks, or the gradient divided by the Hessian. And it looks quite messy. And it's, this is an exact representation of it. There are ways of writing it where you use approximate Hessians, evaluate at the current iterate or things like that. Or at the initial iterate, and then we get slightly different equations, but also introduce approximations. But the exact one looks like this. And the first thing you notice is that you have the inverse of the covariance matrix for x here. You have the inverse of the covariance matrix for x at the iterate here. And again, it comes back here. And this you have to compute. And of course, we only have an ensemble representation of these, so meaning that they are low rank. So you have to introduce pseudo-inversions. So in the best of cases, you will have to compute a pseudo-inversion of the full ensemble in every iteration. You can reformulate it to only do it on the initial time, but then the method becomes more approximate. That's and this is an expensive computation if you have a large ensemble with a huge model state. Okay, again in this equation we also use this regression representation. Okay, so here we should have had the tangent linear model in this CXY terms, and they are now replaced with covariances. So that's another approximation that means that you will slightly deviate from the exact minimum of the cost functions. But it appears to not be a very strong approximation. Also, when these are low rank, then the estimates of your sensitivity might not be very good. They might be noisy. Although it's stable, but it might be noisy. it's also interesting to see that this CXX is just defined as divided by n minus 1. So this is the covariance matrix for where here you have the ensemble anomalies, okay? And that means that the leftmost matrix here is an A, CXY is equal to, and then you have Y divided by n minus 1. So here also the leftmost matrix is A. So that means that, yeah, so the leftmost factor of the gradient is the ensemble anomaly matrix. So that means everything you do is proportional to this ensemble anomaly matrix. So you search for your solution in a space that's spanned out by the ensemble anomaly matrix. And that's quite important, because then it turns out that you can get rid of this gradient and search for the solution in the ensemble subspace. I wanted to ask? No. Okay, so, and by experience, this has been implemented for reservoir applications, and people are, well, the computational science people are struggling to implement it consistently, and they are making mistakes.
The body factoristic technique may give you some approximation of CXX symptoms.
Yeah.
Directly, is this possible?
Yeah, I have not seen it done except what you are doing, but in principle it should be possible. But I think my point is more that it's possible to do something simpler than this. This term, you know what? This would be the H transpose in the standard gamma filter. It doesn't look like that at all. It would be the CYY in the standard parameter estimation problems. What you can show is that using CYY here, which is what most people are doing, is only okay if you have more unknowns than you have ensemble realizations. If you have less, you need to write this full expression. That's it. You can come back to that if it is important. It's quite easy to see. If you sample, have one scalar, you sample x, an ensemble of x, you have a nonlinear function, compute the y, and you compute its covariances, and you will see that CYY is not equal to, yeah. Okay, let's see what we are solving again. This I showed also earlier in the meeting. This is a linear cost function, and it's an ensemble, iterative ensemble smoother. And I start with a prior value for each of these cost functions. The ensemble smoother update goes directly to the minimum. The iterative ensemble smoother goes stepwise to the minimum. And the solutions are exactly the same. And these are things that's nice to know, right? It's nice to know that the ensemble smoother and the iterative ensemble smoother should give exactly the same result for each realization in the linear case. Because then you use this as a test in your code later on to make sure that it's converted to the right thing. In the nonlinear case, that's not true. And then you see that in this case, the ENKF solution ends up here, here, no. But so they are not the same, right? We go here. The iterative smoother goes closer to the global minimum. But here you can see that it's not exact. Maybe it should be even a bit in this direction. And this is the approximation where you started to use a sensitivity matrix for the adjunct. So that's the effect of that approximation. But still, it's not a huge approximation. So that means in this case we will have an approximate sampling of the stereo. Okay, so what I will do now is to go through an algorithm that we just recently published. And the motivation was just that the old version of the iterative ensemble solution was so difficult to implement and also computationally much more expensive. So now I define my axis. This is the prior ensemble, put them in here. I have the measurements, put them in D. I have the ensemble mean, the ensemble mean of the measurements, the curve measurements. And I have the ensemble anomaly matrices. And then this looks a bit bad, but this is identity matrix of dimension n. This is 1, it's just a vector with only ones. So if I multiply with the transpose, then I get a matrix that's n by n and has 1 in every element, okay? And then I multiply with 1 over n. So it just means I'm subtracting the mean. So this expression is just subtracting the mean. It's a projection, okay? Operator. And then I introduce the scaling here because it's my definition of covariance matrices are really simple. So I don't have 1 over n here. So, and then you have the same for the measurements. These are measurement perturbations, and this is the error covariance matrix for the measurements. Okay, so this is my cost function, and I want to minimize this. And what I do now is to search, because I knew that the solution is supposed to be contained in the ensemble subspace. So I search for the solution in the ensemble subspace, okay, or ensemble space. I say that my solution is the prior for each realization plus a linear combination of ensemble anomalies. Okay. So, and this, now I only have to solve for this linear combination. So I have, if I have 100 realizations, I have 100 coefficients in W to solve for. And I have 100 for each realization in the ensemble. So I will put this one in here for X. And then this first term becomes really simple. It's just W transpose times W. So CXX is gone. It's out of the equation. And here I get, I just put this straight in for G here, so it didn't change much. And this is a bit similar to your equation earlier this morning, right? Yeah. I think we used the mean here, but that's just a technical thing. And again, we use a gradient method to solve this. And what happens now is that you reduce the size of your problem from the number of parameters, which is this n, to another variable, which is the number of ensemble realizations, which is much less than the measurements and much less than the same. So you have a much more compact and small problem to solve. Okay, and we are going to iterate these W's like this. So that means I need to compute the gradient of this one. And if I want to use Newton method, I also need a Hessian. And those are easy to derive. So this is just my gradient now, and this is my Hessian. Again, now I have this term in here. Again, I have the tangent linear operator of the model evaluated for each realization. And I could use the adjoint equations to compute these sensitivities. Okay, then we'll have to do one backward integration and one forward for each realization. But we are going to introduce this regression term again to get rid of these adjoints. And this is where we spend a bit of time to solve this. Okay, so if I put in everything into the iteration scheme, I say, and here I also used the Woodbury lemma to get it over in the Kalman gain form. But then we have this increment. As this matrix is the same as the Kalman gain matrix times the residuals. So this is D minus the prediction, and you have this correction term that also comes in. So if I put this in here, then I have an iterative scheme. But I need to figure out what to do with these GIJs. I published some papers where I tested this on simple scalar equations, and then I also computed it using the exact analytical expressions, so with the full GEIJs, and to kind of visualize the impact of using a regression. But I don't think I will discuss that more now. Okay, so we have to look at this term, and that's just the gradient of the model evaluated at the current instrumentalization. Okay, I think I showed this quickly the other day, but then I have a simpler version of it here. So the first thing we do, we replace this one, GEIJ, with an average sensitivity. I is not an iteration, right? So in each iteration, we have an average sensitivity. And then we define a linear regression. So we relate G times A with Y. So this is a standard expression. And it's now written in the ensamble. So I have an ensemble of ensemble anomalies. I have the ensemble of model predictions. So Y is just the model, integration of the model, subtraction of the mean, and division by square root of n minus 1. And then I write, so then I take this original expression, I approximate it with the one with the average sensitivity, and I put this G in here, so I get Y, AI plus, and A. And when you look at this, it seems like you still have to compute this pseudo-inverse, right? Because you have it appears here. But then I'm going to use another little trick, because I can derive this matrix, this transition matrix omega, which relates an ensemble of anomalies at iteration y to the initial ensemble of anomalies. And this omega is just this equation here. In the paper, it's just a few steps to show that this has to be true. So, and this one is invertible, so you can multiply from both sides. And now I can take this A and I can replace it with AI and omega I inverse, like this. And the cool thing now is that this expression looks like this. So this product is an orthogonal projection. The only thing it does is to remove the ensemble mean. And Y has already the ensemble mean removed, meaning that it doesn't do anything. So I can write it just Y times omega I inverse here. And this is true. It's always true if the model is linear. It's true if you have a state size larger than ensemble size minus 1, which is normally almost always the case. If it's not the case, then this product is so fast to compute that it doesn't matter. So we are really interested in this regime here. So that means when you get rid of this, then you end up with an algorithm which is independent of the state variables, which is quite cool. And I call this product for, I call it S, so in the equations hereafter. This is just explaining why this is true, so I skip that now. So, okay, so we end up with an iteration for omega, or W I call it, containing all the omegas. Use W initially. Yeah, it's the capital W representing all the small W's. And it looks really like similar to what you have in the Kalman filter, right? You have a Kalman gain type equation here, except that it's a bit different. It's the predicted models at iteration y, deconditioned back to the initial time. And then you have the residual, and you have this correction term. Okay, so let's look at a special case. If you are at the first iteration, then this W is 0 initially, meaning that you start from your prior. Then, if W is 0, Wi is 0, so then this disappears. Omega will be equal to the identity, so this is just the y's. And what you have here is, and this one disappears, it's exactly the Kalman filter update, if this gamma is equal to 1. So that means this scheme also solves the ensemble smoother update, using just one update by starting with omega or W equal to 0. Okay, so and that's useful because then you can use the same scheme whether you want to do a Kalman filter run or you want to do iterative smoother calculation. And the way we write the algorithm is like this. The only inputs you have is the ensemble of state variables and the ensemble of measurements. This could be used, but then we are not using it. We start with W1 is equal to 0. We run, and then we have a loop here. So in each iteration, we have to integrate the ensemble forward in time, subtract the mean, and scale it by n-1 to get these y's. Then we use the current value of of W to compute omega, and it's quite easy. You have this one, and subtract the mean and scale and the identity, and then we solve these systems of equations. And this is one factorization. It's a square root. It's the ensemble size square, the size of the matrix, and you need n back substitution, one for each measurement. But it's linear in that. So it goes quite fast. And when you have S, you compute this product. And yeah, you evaluate this right-hand side, and you have everything you need in this equation. So the issue then is how to solve this one. Because now we have to compute the inverse of this, and this matrix is the size of the number of measurements squared. And the number of measurements is much more than the ensemble size. But then, why would you invert a matrix the size of the number of measurements if you only want to compute n coefficients, one for each realization? So in a way, here we are doing way too much. So I will show you how we are dealing with that particular computation. The important thing is that you can do all of these things linearly in the number of measurements and in the state. And I have no approximations of the CD. It can be completely full or not the other. And when you find the W, you just update it. Then you multiply this transition matrix with the initial ensemble to get the updated one. And it's nice to know that in here there is no reference to the state space or state vector. So whether you do this for a scalar state variable or 1 million or 10 million, these computations are independent of that. They don't care about that. Yes.
Have you ever thought about this, such as a learning problem? Because from my point of view, it was like a solution as a delta rule or a stochastic gradient descent algorithm. It's kind of clear to me that what we are doing is trying to searching an optimal solution to the optimization.
Yeah, it's an optimization problem.
Yeah, but this is more or less like a learning algorithm.
Yeah, but
Because
these things are so similar, right?
Yes. So, and my concern is about this coefficient of learning that I would call like a learning rate. What do you have?
You mean the gamma?
Yeah.
Yeah, that's there are different ways to handle this. I have used in the rest of application to use the gamma typically like 0.6 instead of 1.0. If you have 1.0, then you get 2 violent updates. So
you may add a momentum one.
And so actually the scheme I have now starts with 0.6 and then it goes down to 0.3 quite over 5-6 iterations, 7, 8, something like that. But that's a tuning. and it's not the optimal thing. I think I will also, when I have time, start looking at adding a coefficient in front of the C, meaning that if this is a coefficient larger than 1, so if you put 10, and then it kind of decreases slowly towards 1, then it means that we're introducing the measurements more slowly. And I'll show you why in a second. I don't know how interesting this is, but this is just my first scalar test to check that the method is working, and it gave the right result. So you have a Bayesian solution, which is this black one. This is a nonlinear problem. It's a nonlinear scalar problem. The code for this is a Fortran code, and it's on my GitHub. So if anyone likes Fortran, I can look at it. Fortran is a way of making sure no one ever looks at your code. Okay. This green curve is the exact solution of the iterative smoother, where I solve it in a state space using 7 means it's 10 to the power 7 realizations. So I have 10 million realizations. And then you can get very accurate estimates of the PDFs. And then the problem now is that in this new algorithm, I have all these terms that are quadratic matrices the size of the ensemble, right? So if I have 100 realizations, this is a 100 by 100 matrix, and it's not a problem. If I have 10 million realizations, then certainly this becomes an issue. But it's not a regime I'm interested in. But anyway, it means that in my tests I could not use 10 to the power 7, so I went to 10 to the power 4. So I have a 10,000 by 10,000 matrices instead. And then the iterative ensemble smoother with 10,000 errors is the blue line. And then using the new subspace formulation, I have this red line. So I'm exactly reproducing the results from the, whether I do it in the ensemble subspace or in the state space. And this was just the first test of that. And in fact, you do it exactly realization per realization. So the methods are identical. It's just that this is so much faster and easier to use. And yeah, this is what you see. If you look at the different iterations, I start from the prior here, and then this is iteration 1. And you can see it's a bit maybe too violent update. I would rather have something that looks like this, and then like this. So it kind of moves slowly towards. And that, I think, this Lovenheim iterations would help on that. Because then I more gradually introduce the measurements. So we're going to try that. And the nice thing with algorithm is that you can actually test everything in a scalar case, because it's independent of the state size. It's only dependent on the ensemble size and the nonlinearity of the model. Yes. Okay, let's. I'm not going to keep track of time because then I get nervous. So I just continue until you stop moving.
Yes. Nobody will stop.
So I almost asked you about the red matrix there and the Woodbury matrix identity.
Yes.
Because in that way you can put everything onto the ensemble space, so it will be very cheap to compute.
Yeah, in this case, it's scalar case.
Yeah.
Yes. But I'm not interested in the scalar case, really.
No, I mean, if you project everything onto the ensemble space by using the Woodbury matrix identity, that's actually what you do there.
Yeah.
The inverse, I mean, it doesn't cost, it doesn't have it doesn't require high computational effort.
No, and that's what, okay. So this is the standard form.
Yeah.
And if you actually wanted to compute this C is full.
Yeah.
And you have to compute this product, construct the full matrix, and compute the full inverse. It's just brute force, it's m to the power 3 computations. You can do it more efficiently, but then you have to use more fancy numerics.
The composition.
Yeah. Maybe approximate numerics, I don't know. But it's possible to deal with, but I should know that this end is really big, okay? Yeah, that's what I do know. It should be so big I don't know what to do with it. If you use Woodbury, then you can rewrite this equation on this form. And the nice thing now is that this inversion here is in the ensemble space, so it's n squared. It's not n, this is n squared. measurement square. This is ensemble realization square in size. Still, you have to compute the inverse of the error covariance matrix for the measurements. But what everyone in the community is doing is to say that, no, let's approximate this one with the identity matrix. Okay, it's diagonal. And if you do that, then the equation becomes like this. And this is just a matrix, this ensemble size square. You can solve it easily using any MATLAB code. And yeah, so you have a really simple way of computing these iterations. But now you've actually made a serious approximation that you will have to live with or understand the impact of it if you understand. And it does actually have an impact. It's, there are lots of applications where you cannot write this. It can lead to overfitting measurements and all kinds of strange things. Okay, so that was the straightforward thing to do. This is what I'm doing right now. And the reason I'm presenting it is that it's an old algorithm, it's 15 years old, and no one is using it except me. So now I'm starting to introduce it and present it again. Okay? It's not entirely true, but it's not far from it. Okay, so this first question: why invert an n-dimensional matrix when you solve for n coefficients? That's the motivation for it. We never form the error covariance matrix for the measurements. We sample perturbations of the measurements that represent these errors. And it's much easier to sample these perturbations than actually to construct a positive definite error covariance matrix. So, yeah, so that's the strategy. If we do that, then this term, S transpose plus CDD, becomes like this. And if we make one assumption more here, namely that we can project these measurement perturbations onto the space spent by the predicted measurements. Okay. This is a projection operator, so I just put it one there and one there, meaning that now I take my measurement perturbations, project them onto the ensemble subspace. Okay, then that means I'm changing something, and there are issues with this, because if you were, for some reason, sample all your measurement perturbations orthogonal to the ensemble subspace, then they disappear. But in fact, that also happens in reality if you have a subspace representation of the error covariance matrix. Okay, so let's compute, go back to, where are we now? Look at this one. Okay. If you use an SVD of S, U sigma V transpose, multiply it with the pseudo inverse, so then it's V transpose times V times sigma plus times U transpose, I think. Yes. Then you can insert that here for this one and this one. And then you can take the U and the sigma, put it outside on both sides. So if you multiply these together, then you get back the identity. Then you get back this SS transpose here. This expression is quite fast to compute. Assume now that you just multiply these together, you get a big matrix, size of the ensemble, and you do an eigenvalue decomposition. Then you can put this set outside as well. So you end up with something really, well, completely diagonal and the size of the ensemble in here. And this is easy to invert, right? Because these are unitarian, U and set unitarian matrices, and this sigma, then you just use the pseudo inverse for that. So that means you truncate, it's diagonal, you just truncate from the small singular values. So then you have an expression of this inverse term that's computed linearly in the number of measurements very efficiently, and you can handle arbitrary sizes of the measurement vector, and you can handle correlated measurements, and there is an equation. If you go back to me. If you look at this equation here, what we're doing here is actually to project C onto the ensemble subspace. So you're actually using this approximation implicitly in the schemes without knowing it in most cases. Here's the inverse, but they are related. So then we made some tests to see how this worked. I created a linear problem where it's a polynomial and I want to estimate A, B, and C. And this we did in the full reservoir simulator, so it was just to test operational software. And I assume that A, B, and C are Gaussian variables. We can also use other distributions for them, but then it becomes a nonlinear problem. But for the linear problem, then we know the solution, so that's nice to test on that. So I have measurements, 5 measurements at different values of x. So basically what you're trying to do is to fit this curve to these measurements. And we know that the ensemble smoother will solve this problem exactly because it's linear. So we know what the result is. And then, I was showing this before. So I have an initial ensemble for the different coefficients, and I compute the solution using the ensemble smoother. Then I use the new iterative scheme with step length 1 and 1 iterations, and get this red one. And here I do the full iterations. So you see at 5 iterations, 4, 5, there's no real difference between any of the methods. They all give the same result. And to really make sure that this was the case, I was plotting, this is A and B and A and C. So I'm plotting the realizations on top of each other from the ensemble smoother, from the iterative method with 1 step, stepping 1, and that's red, and then with iterations. So that will converge realization to realization to the same result. And then in this software development process, it's almost like a commercial software, but it's free, so you can find it on GitHub. We are using what is called a test-driven development. So that means every subroutine you make has a test. And because you know if you have a subroutine, then you will send something in and you get something out. And if you know what you're doing, you should know what comes out if you know what goes in. It's actually solving a particular problem. So you make these tests where you run the subroutines on small mini examples like 3 by 3 matrices, etc., where you know the input and you know the output, and you check that the computed output is correct. So this is done on all throughout the code on all these computations. So every time you want to combine or change something in this system now, we are running all the tests, and if one test fails, you are not allowed to adapt the new code. And I was building quite a number of these tests in this process of this software, and we had an old version of this iterative smoother, which is, we call it ENRML. And when I run the tests on that one, this is what you get. So here you can see that the blue ones are the ensemble smoother results, so that's the exact solution, and the red is the result of the previous implementation. So then it's wrong. And it turns out that the mean seemed to be okay, but the variance is much too reduced. So that you could just identify with this simple example that no, the code is not working. So now we are removing it from the software. We were not able to find the bug. Yes, so that's just to advocate the use of test-driven developments. The other problem I have with this is that in the research community, you see so many presentations, and it's really obvious that they did something wrong. There is a mistake in it. This cannot be true, because it's not consistent with what everyone else finds, so things like that. There are so many papers and presentations where this shows up. And if you program in Python, there's something called PyTest. Who knows about PyTest? Yeah. In C, it's something called C-test. And it's a really, it takes a bit of effort to write all the tests, but it saves you a lot of trouble. So that's, if you don't remember anything else from this presentation. Remember that. Yeah, this is a case with a reservoir model, and I'm plotting all the cost functions and also the average cost function as a number of iterations. And it's a log scale here, so you see quite well what's happening. And you can see that after 5-6 iterations, it's converged. At least it's converged to a level where a reservoir engineer would not really care running more, because they need results quickly. So it means that we have a method that can give you a good result in quite few iterations. Yeah, it also has a quite nice convergence. And what we did to tune this gamma factor or the step length is to look at these at the behavior of all the individual cost functions. And if we have very many cost functions that increase the value between two steps, then we go back to start and reduce the step length a little. So that's how we ended up in this case we ended up with 0.6. And that's something that seems to be robust with if you have 100 realizations. If you go to 1,000 realizations, probably you will go to 0.7. 10,000 realizations, 0.8. At least that's what we could. That's something we could see from this scalar example when we invested it there. So it's dependent on the sample size. This is the average cost function for 3 cases, and basically there are 2 that's interesting. Was the first one, then now we are assuming that the error covariance matrix is diagonal. Okay, so we can use this scheme with exact inversion. Then we can use this scheme that solves the problem exactly without any projection of the error covariance matrix. So that's the one case. And the other case is when I use this expression for the inverse. Okay? And in the case with diagonal error covariance matrices, the results are the approximate one is the violet one, and the green or blue is the first exact one. So basically they have the same behavior in the cost function. If you look at the estimated parameters in the three cases, then you have this is just there are 3 different fold multipliers in the model. So you start with an initial ensemble, and the 3 methods give these ensembles of parameters. So you can see again that they are essentially the same. So this fold is closed, almost. This one is mostly closed, but not as close as that one. So, but they have basically the same behavior. So the approximations are not really impacting the results. Again, this is the production profile. So you have the initial ensemble in the blue for 2 different wells, and the red is the posterior ensemble of production profiles, and there's a black line in here that's the measurements. And the upper and the lower are just the 2 different inversion schemes again, the exact one and the approximate one. And again, you will not really see a difference in the results. So I presented this new subspace implementation of the iterative ensemble scooter. You could ask why we will not use square root formulations or other methods, but I kind of like this. I like to formulate the problem as a sampling of the posterior, and then it's just a stochastic sampling of the posterior, and that's exactly what we are solving here. And then we saw that this duality between the sequential data assimilation and the inverse problems, we can use the same method. Now we could solve this problem by iterating here until you have convergence, and then the estimate here would be the optimal. So And in my opinion, this is significantly going to improve the results in sequential data assimilation if you do these iterations, and then you can afford it. Yeah, and we have an algorithm that's formatted for big data sets and big state vectors, because they are linear in both. It's important. There are 2 papers describing this. This is a theoretical paper that we wrote. It's mainly me and Patrick Ruonis that have done this work. And then we wrote one paper which is more aligned with this presentation to give a simple introduction to the method and implementation. And it's already available operationally in this what we call ensamble reservoir tool, which is used for reservoir history matching. And there is some paper there. I'm sure you will all get access to this presentation, right? So then it's possible to click on these links. So this is, if you click on this one, then you, yes, then you go straight into the Git repository where the implementation, this is the IES, it's an iterative ensamble smoother algorithm is implemented. And this is a C implementation with, it's kind of in a macro, written in a macro language way, but it's possible to have a look at the routines. Yes. I don't know how to get back. I have no idea.
Do we have some questions for Professor Evensen?
Yes.
Hi, my Professor is nice to meet you. I'm from Ecuador. Ecuador is the global petroleum company. Is interesting this point of view where you use an attention time of the state. I have some qualitative questions. For example, the tests that you are conducted are only for update static parameters, or also to update, for example, dynamic parameters or dynamic state like saturation, like pressure.
In the reservoir, we are not updating the dynamic parameters. We used to do that before, doing ensemble gamma filters with reservoir models, but we got into issues because we update the parameters and the dynamic variables at the same time, and to make everything consistent.
Yes.
You have to have a clear mind and.
That's the other question.
Yes.
How do you test the consistency of the solution? Yes, because for example, the pressure is a dynamic variable that is it needs to have a consistent with the propagation in space.
This is exactly the questions I would get from the reservoir engineers in Equinor and Statoil when we introduced ensemble filters for history matching. And there are other things I didn't like, that suddenly you change the volume in the reservoir.
Yes.
And that you're not allowed to do, even if it's wrong. It's a politically decided value, and you cannot change it because then your shares go either up or down. So, but anyway, what happened was that we abandoned the use of EKF for reservoir history matching and start using smoothers. So what you do then is that you only update your initial model, and then you run your realizations. So it's only the static variables that are updated.
Okay, you only will be the static variables.
So we are in this setup.
That's the problem for this matching.
Yeah. And the other thing was that for the rest of the engineers, it made more sense for them to go in and change the static variables and then run the model, because all the other commercial software is doing the same. Like MEPO, and they only estimate the model's parameters and then they run the models afterwards. So if we could do the same with the ensemble methods, then they certainly understood what we were doing. They could look at this better forecasting way of thinking.
For example, what problem we have is that it's difficult to establish a common or a limit for build ensembles. For example, how we can establish the probability solution to build the ensemble. Because there are many unobservable variables. That's the question. The question was that if you have to test with dynamic variable, dynamic states. The other question is, you mentioned that you update in time parameters. How long do you consider that time? For example, 1 month, 1 year.
I can answer that, but this is useful for weather forecasting or like weather prediction, meteorology.
Okay.
Yeah, for reservoirs, I would still be there on the.
Okay.
And in the atmosphere, this will typically be 6 hours or 12 hours windows.
Yeah, but for the several application, you don't.
Well, then here it's different, right? Because now you have your initial model, the probabilities, etc., and you predict the produced oil for 10 years, for example, and then you have measurements of the produced oil, and you use this to update.
Well, for example, the value of measurements in reservoir is around 1 month that the Colombian law requires that measurement in fields, right? So the measurements are available in month.
Yeah, but normally you will not update your model every month. If you do, you would be too smoother. You have to go back to start and integrate again.
Oh, okay.
You can
You
either
perform history matching first and then apply the ensemble camera filter to conduct the prediction.
You can do different things. You could use the ensemble camera filter, update it recursively with new measurements, but then you get into the same problems as I had before. Typically, what we used to do in Equinor, still do, is that you have maybe annual model updates where you rerun everything, all the new measurements, new geophysical seismic servers, and you build a completely new model. And then you use this for making all the economic predictions and planning new infill bands, etc. for the next year. So there's a kind of annual maturation process, and you use this as part of that. And there is another issue of these recursive measurements that come, say, monthly in time. If you look at the measurements 2 months next to each other, they don't necessarily have new information. It's more the same information coming again 1 month later. It doesn't add new information. There's a lot of redundancy in this time series of rate data. I wrote a paper last year on exactly that topic, discussing these things. But you know, you're actually running this in equal control now.
Yes, I know that topic. We are working with a topic that you work that is called reservoir management, but we are trying to adapt this approach for short time time. Yes, you use this approach for long time, similar for history matching. History matching is a problem that is treated for the audience. We are working most on optimal control operation as well, yes, or well control and optimal operation. I know that you, for example, this topic is used for uncertainty management. I think that for uncertainty management. But well, the topic is not easy to implement.
But this workflow, this software for using ensembles for uncertainty prediction, for conditioning and optimization, is operational in all the Equinor fields. It's used in every field now, from early field development into late phase. And I know one reservoir engineer in your company who actually installed this and is playing with it now. So you're
yes, I know that with our leader in control, I know that you go to visit the installations and to know more about that. But we are going to do some tests with this, and also with some approach presented by Stanford, the Professor Jansen. We use some approach that is available in Syntef software, the software by Syntef, and some tests, but maybe we are not understanding so well how to use in the specific field, right? Because we are